Good morning, everyone, and thank you for joining us. Welcome to today's webinar, AI-driven archaeology with LLMs, detecting archaeological sites from aerial imagery, organized by NCC Slovakia, in close collaboration with NCC Portugal as part of our LLM webinar series under the EuroCC project. My name is Božidara Pellegrini from NCC Slovakia, and I will guide you through today's session. Before we start, here are a few quick technical notes. To ensure a smooth experience and high recording quality, all participants will remain muted during the presentation. If you would like to speak during the Q&A session, please raise your hand and we will unmute your microphone individually. And you are also welcome to use the chat at any moment. Today, we will explore how multimodal AI, vision transformers, and LLM-inspired methods are being used to detect archaeological sites such as burial mounds and hill forts from aerial and LiDAR imagery. These techniques significantly reduce false positives and enable more efficient large-scale surveys. Now, let me introduce you our speaker. Dr. Daniel Canedo is a research fellow at the Institute of Electronics and Informatics Engineering of Aveiro, University of Aveiro. He specializes in computer vision and artificial intelligence with publications in international conferences and journals. He is also the winner of the NATO Stratcom Innovation Challenge and has experience applying advanced machine learning methods to complex geospatial and archaeological tasks. So, Daniel, please, the floor is yours.
Thank you, Božidara. Let me share my screen.
Yes, we can see it.
Okay, so good morning, everyone. So before I start, I want to thank you for the invitation. It is a pleasure to be here. I'm not going to introduce myself because Božidara already did a good job on that. So today I bring you guys a brief presentation about how you can detect archaeological sites from aerial imagery using AI, more specifically vision transformers. So this is the outline of the presentation. I will do a brief introduction and motivation. Then I will talk about the challenges of detecting archaeological sites in aerial imagery, vision transformers. Then, as Božidara said, I will explore two use cases, burial mounds and hill forts, and then finally the conclusion and future directions. So this work derived from a research project called Odyssey. The consortium for this research project was composed by two universities, University of Maia and University of Aveiro, where I was included, and also an archaeology company called Archaeology from Portugal. The main goal of this project was to develop a platform that could aid the archaeologists during their day-to-day work. And the work package that I was involved in was responsible to develop an AI service to be integrated into this platform, where the archaeologists could submit images, and then our AI module should be able to detect or try to detect archaeological sites on those images. And then obviously return the locations, the real world locations, to the archaeologists so they could go and search for them during their fieldwork. As for the challenges for this work, we had a lack of publicly annotated data. We had a lot of LiDAR data, but the data was not properly annotated. Luckily, we had archaeology company by our side that had some knowledge about these archaeological sites, and they could provide us the location so we could annotate the data. these kind of solutions are always prone to false positives due to the aerial perspective of the data. Because of the top-down perspective, we are only able to see the top part of the archaeological sites that are easily confused with other elements in the landscape that happen to have the same shape or resembling shape. This is problematic not only for machine learning models, but also for expert archaeologists that have trouble dealing with these similar shapes in the landscape. The data is quite heavy, which causes processing and storage challenges. And since it was an emerging area in computer vision at the time, we started this project like 3 years ago, I think. It had a few publications that could inspire our work. And before moving on to the use cases, it is important to clarify the main technology that we used to make a breakthrough in these research fields, which is the vision transformer. This technology utilizes the same principles of large language models, namely the transformer part. And what vision transformers essentially do is basically dividing the image into fixed size patches, and you can see these patches as words in a sentence, and the sentence being the whole image. So these patches have a position and a meaning within this image. And of course, those two things are quite important when the transformer attempts to learn the relationships between all the patches during the training step. And up until this point, convolutional neural networks dominated computer vision solutions, but vision transformers came in around when ChatGPT started to gain popularity and demonstrated equivalent or even better performance in some cases. Well, as for the first use case, we attempted to detect burial mounds. You can see how they look like in this image. They were constructed between 9000 before Christ to 1200 before Christ. Of course, this isn't the type of images that our vision system is going to tackle. As I mentioned before, the perspective is aerial, so we only see the top part of these archaeological sites. As for data collection, our archaeologists conducted some LiDAR surveys using a drone, and we also had access to some LiDAR datasets from Portugal and Spain. In Portugal, specifically, we had access to a LiDAR coverage from Alto Minho, and in Spain, we had LiDAR coverage from Galicia. So, as many of you may know, LiDAR data are essentially 3D point clouds, which is quite heavy on the storage. So what our teams did at the time was to process this data in order to reduce the dimension of the data. And so they processed it to obtain these digital terrain models that you can see on the left image. Then we applied a visualization technique onto that digital terrain model. And the visualization technique that we chose at the time was the local relief model. And we chose this model because it highlights micro-topographies in the landscape, which is crucial to try to detect archaeological sites. And finally, we can annotate any archaeological site that we have knowledge about. And you can see that in the right image. And we basically annotated those archaeological sites with by drawing a polygon around them. Then, well, we needed to build a conventional data set for AI models. As you can see in that table, the images that we had access were quite huge. And if we tried to feed these images onto an AI model, we would get GPU and memory problems. So we need to break these images down into smaller images. to build a conventional data set. And for that, we built a simple algorithm that would iterate over every annotation that we had and generate a cropping window around those annotations that you can see painted as yellow in these three images. And this cropping window would crop an image if that image respected two main criteria. The first criteria is that the archaeological sites must be fully visible within the cropping window. And the second criteria is that archaeological sites that were within the cropping window should not have been saved in a previous iteration. And so you can see that algorithm working in these three images. The annotation that serves as an anchor for this cropping window is painted as green. And in the first image, you can see that it doesn't respect the first criteria because it's cutting two archaeological sites. In the second image, it's not respecting the second criteria because we have two archaeological sites painted as red that were already saved in a previous iteration. And in the third image, it respects all the criteria, so the crop was made. And then we proceed to the next iteration of the algorithm. And we do this for all the annotations. And so in the end, we have uniform and organized conventional data set that we could use to train an AI model. So you can see here a summary of what I just talked about in the diagram. The only thing that I didn't talk about was the LiDAR cropping. So every time we saved an image, we also went to the raw LiDAR data and we cropped the 3D point clouds of each archaeological site. And that would allow us to utilize 3D features down the line to try and validate some detections. But I will talk about that later. Since we had our data set had a few hundred images and a few hundred annotations, which is not ideal, we basically tried to do some data augmentation. We did two approaches. The first approach was a traditional data augmentation where we did random geometric and color transformations. And you can see what resulted from it in this table. And the second approach was a copy-paste data augmentation, where we basically crop an image from the local relief models that intersect a region of interest outlined by the land use and occupation charter of Portugal. And I will talk about this in the next slide. Then we run a simple YOL model that was trained in the original dataset on those few hundred images. That this model is quite sensitive, so it would detect anything that resembles an archaeological site, but that was okay for us because we just wanted to make sure that the images that we are cropping do not have any unknown burial mound there. So we can then paste our own burial mounds to that image. Then we apply geometric transformations to both copied burial mounds and cropped image. And then we paste the burial mounds onto the cropped image within a region of interest. So what I mentioned before about the land use and occupation charter of Portugal, you can see how that looks like here. We have that charter on the left. Each color represents a class. And with these classes, we are able to basically remove the classes that are not relevant for archaeology and just use the ones that, well, there is a non-zero possibility of having an archaeological site. And we use this to basically, so our data augmentation pipeline remains consistent with the real world. So we don't copy burial mounds onto rivers, for example, or buildings, cities, etc. So you can see in these two images that burial mounds would only be pasted onto green regions. And so we would avoid, for instance, to copy burial mounds onto that river or onto those regions around the river that I think were a small city. And this is what it looks like. These burial mounds do not exist in the real world. It's basically our augmentation process. And this is basically a summary of what I just talked about. And in the end, we chose to keep this copy-paste data augmentation approach instead of the traditional one. And you can see how we were able to exponentially increase the number of annotations with this approach. After that, we trained a YOLO V5 model, specifically the medium network, as a compromise between performance and speed. We trained three models, three YOLO V5 models on each generated dataset. The original one that I already talked about, that we trained that YOLO V5 model to check for burial mounds on those cropped images. Then we trained another one on the traditional augmentation dataset. And lastly, we trained another model for the copy-paste augmentation dataset. And we did this so we can compare these three approaches and see which one was more suitable for our problem. Well, and you can also see the hyperparameters that we utilized during the training. So after the training process, we needed to develop the deployment pipeline. And this deployment pipeline starts with a sliding window that sweeps through all the data that cover the testing region, and the resulting cropped images are fed to the YOLO V5 model. And we also had a post-processing validation block that is divided into two steps. The first step is the same location-based ranking approach that we used in the copy-paste augmentation pipeline. But in this time, instead of pasting burial mounds, we are just putting the location of the detection onto that land use and occupation charter of Portugal and see if that location makes sense or not. And the second step is a local outlier factor, which is an unsupervised anomaly detection method that was trained on those 3D point clouds that we saved previously of the burial mounds. And in each detection of our algorithm, we would go to the whole LiDAR data, make the same cropping of the 3D point clouds, and then feed those onto this local outlier factor to see if the 3D features of that detection resembles the burial mounds. And well, you can see a summary of this inference and post-processing validation pipeline in this slide. So as for the results in Altomínio, you can see how each approach impacted the number of inferences in the first table. So the model that was trained on the original dataset, where we didn't do any data augmentation, had around 3,400 inferences. The one which was trained with the traditional data augmentation, we were able to reduce many number of inferences for 1,500. With a copy paste, we were able to reduce even further to 1,467. And then as I mentioned before, we decided to stick with the model that was trained with a copy-paste data augmentation dataset. And then you can see how each post-processing step impacted even further the number of inferences. And at the end, we have 648, which is much less than what we originally had. And that's quite important because we want to provide the archaeologists the least possible number of inferences. We don't want to provide them thousands and thousands of images and inferences. because they need to do field work to find them, and it's not reasonable. And in the second table, you can see the digital validation that was conducted by 4 expert archaeologists on these 648 inferences. And they reached the conclusion that 470 were potential true positives, 178 were false positives. And you can see how that looks like in this slide. These were the images that our expert archaeologists used to validate these inferences. And these were the ones or 3 examples that were considered as potential true positives by our archaeologists. I say potential because it still requires field work to actually confirm their existence. You can see here in this slide 2 examples of false positives. The main culprit was rock outcrops. And as you can see in the left images, in the local relief models, the shape of these rock outcrops, at least in these instances, are quite similar to burial mounds. I can pull back the slide so you can see. They have kind of a circular shape with a black dot in the middle, and this was enough to confuse our model. But when we see the satellite images, well, they are just rocks and they are not burial mounds. Another point of failure for our vision system was an inconsistent land use and occupation charter of Portugal. You can see here that our model detected 2 roundabouts, and these detections should be removed by our first post-processing step, but they weren't removed because, as you can see in the 2 images on the right, the red color is basically infrastructures like streets, buildings, etc. And well, it's inconsistent with the real world because these red colors do not match with the streets that we have here. So because they didn't match, our detections were placed onto a region that has a non-zero possibility of containing archaeological sites, which is that yellow region, which represents an agriculture region. And so they passed that post-processing step, and well, they were false positives, obviously. So after this work, we were still not satisfied with the results, so we attempted to refine the system, and we introduced 2 new blocks, a slope filter and a vision transformer model as a post-processing step. For the slope filter, we follow the suggestions of our archaeologists. They essentially said that burial mounds were usually constructed in flat surfaces, and because of that, we chose to apply a slope filter. And in this slope filter, we basically went to every annotation that we had, and we expanded the bounding box, the annotation that we had for those burial mounds. The expanded bounding box is represented with green, and the original annotation is represented with red. And the idea is to try and see the slope around the burial mound to see if they are indeed in the flat surface or not. We basically do that by making an average slope, utilizing all the pixels between the green bounding box and the red bounding box. And you can see the distributions there on the right side, and indeed they are usually in the flat surface. So we can define a threshold to remove any detection that is not in a flat surface. As for the second block that we introduced the vision transformer model, and this was inspired by the digital validation that our archaeologists did. we thought that, okay, we can maybe utilize a model to do this work and try to basically do image classification. We just give this model the detection, and the model is responsible to say, okay, this is a burial mound or not. And for that, we constructed a small data set of burial mounds and some instances of false positives. And as you can see in these images, the first line is burial mounds, and the second line is basically consists of false positives. And of course, we utilized satellite imagery for this model. Well, with this, we hoped that we would enable the system to reject obvious false positives, and that for some reason passed the previous post-processing steps. And we had some success with this refinement, as you can see in these two tables. The slope filter and the vision transformer model were able to reduce the false positives while retaining most of the true positives. This was exactly what we wanted. Each new post-processing step basically helped our overall vision system. And in this slide, you can see a comparison between our proposal and a similar work that was conducted in 2021 in the region of Galicia in Spain. We got slightly better results, but what I want you guys to take away from this is that this showcases the challenges of detecting archaeological sites in the aerial imagery, as these results are, well, they are nothing to write home about. They are not that great, right? But anyway, we were still able to find 23 new burial mounds in Alto Minho that were in remote areas, and 93 additional sites are still under review because the Archaeologia, the company that worked with us, it still needs to do some excavations and some archaeological procedures to confirm that they are actually burial mounds. So as for the lessons learned from this use case, we think that the system was over-engineered. It had many potential points of failure. Too many types of data for different blocks of the system are required, including the raw LiDAR data, which is a nightmare for storage. As I mentioned, the results were not that great. And so we thought that we had to go back to the drawing board, and the whole approach should be reconsidered. And then the Odyssey project ended at that time. But our team was not quite satisfied with the results. We felt that we were close to something, but we didn't quite reach it. Therefore, in our spare time, about 1 year ago, we took a step back and we rethink the whole system from scratch. And we needed a target for this new system. We thought that burial mounds, despite the results that we obtained, were quite more simpler than the other archaeological sites, because burial mounds had kind of a defined shape for the most part. They have a circular shape with a black dot in the middle. So we wanted a target that was a bit more challenging than that, and so we chose hillforts that are essentially a set of enclosures that do not have a defined shape. And this image illustrates how they look like. As for the data collection, we reutilized the same data that we had for burial mounds, but we added data from the UK. We had LiDAR coverage for the whole UK, and we also had the hillfort locations for this region, as you can see in the image on the right. However, these annotations are points, so we still had to make the annotations by ourselves, the polygon drawing. We also reutilized the same pre-processing steps that we did in the burial mounds, mainly the pre-processing for breaking down huge images into a conventional dataset. We retained that part, and we discarded the LiDAR, the raw LiDAR data part, and we discarded as well the data augmentation part, because we thought that it could potentially bias the model towards positive samples, because we are artificially increasing the number of annotations and images. So we thought that we were making the model too sensitive and more prone to false positives. So we discarded those. After having our dataset prepared, which again was a bit small, it had a few hundred images again and a few hundred annotations, we could proceed for the training part. This time we discarded the YOLO-V5 model and we chose a vision transformer, which was called CMX. And this model is capable of adapting two types of data, an RGB image with another complementary image for semantic segmentation. And this is ideal for us because we wanted to replicate what archaeologists do during their digital validation. And so we were able to feed into this model the local relief model image, which highlights the microtopographies in the landscape, and also the satellite image. We can complement that local relief model image with the rich information that comes from the satellite imagery. And then you can see how that training went on this graph. So this is the proposed vision system. It's quite more simpler than the system that we had for the burial mounds. Again, we start with a sliding window to crop a local relief model image. With that sliding window, we are able to extract the real-world coordinates and make a web map service request to obtain the corresponding satellite image, and then we feed those two onto our model. Then we just have a very simple post-processing block that essentially checks for the area of the detections, because Ilforts have a kind of a predefined area, and also a margin filter, because we realized that detections that are on the margins of the image are mostly false positives, because the model has trouble because it detects partially visible objects, confuses the model, and they are mostly false positives. So we discard those as well. And then we have the final inferences. We could stop here, but we decided to introduce a human in the loop process here, where we had expert archaeologists to validate these inferences. So we basically provided the inferences to our archaeologists, and he would say, okay, this is a true positive, this one is a false positive, that one I'm not so sure, and so on and so forth. And with this kind of feedback, we are able to enrich our dataset with more data, especially data where our model failed on. That's quite important, because with this process, we are essentially guiding the model. Okay, you failed in these images, and you are not supposed to. And this helped the model to improve its ability to distinguish between Ilforts and other elements in the landscape that happen to have a similar shape. Okay. So this is an example of the digital validation that our expert archaeologists did. We made a simple script that presented two images to to the expert archaeologist and the inferences on those images. And he basically needed to say, okay, this one is a true positive, which by the way is the one on the left, and that one is a false positive, which is the one on the right. It's a football field. Well, during this human in the loop process, we intentionally biased the data set towards negative samples because the vision system that we were developing was supposed to sweep through tons and tons of data, and the probability of an image to have an archaeological site is quite low. So because of that, we thought that the model should be intentionally biased toward handling abundant negative samples. And this was, well, we were inspired by another work for this idea. And to support this, well, the training data set during that human in the loop process was enriched with basically false positive examples to improve the model's discrimination capability. And as for the results, we were able to significantly reduce the false positives. We originally had 5,678 detections in Alto Minho with that original model that we trained on a few hundred images. And after just one iteration of this human in the loop approach, we are able to reduce that number to just 40, which is a much more reasonable number to provide to our archaeologists so they can do their field work. We were able to also discover some ilforts that were previously unknown to archaeologists, and this solution, at least at the time, which was around 1 year ago, achieved state-of-the-art results with a F1 score of 66%. As for the uncovered ilforts, we were able to find 9 potential ilforts in Jerez, which is in Portugal, and 768 potential ilforts found in the whole UK. And again, I say potential because it still requires field work. And in these 2 images, you can see we have 3 detections. One of them overlaps with a known ilfort from the Atlas of Ilforts of Britain and Ireland, which is marked with a red dot. And the other 2, well, they do not match with anything, so they were considered false positives. However, our archaeologists are almost certain that these 2 detections are also ilforts, okay? For some reason, they are not in the Atlas, or because they forgot to put them there, or, well, they didn't uncover them yet, right? As for the lessons learned from this use case, the vision system that we developed has an high computational cost and long processing times. So processing data from the whole UK on HPC took around 30 days. But the main bottleneck was the web map service requests, because we could not make many requests. We would be timed out if we did that. So we had to put a timer between each one, and we also had to wait for the image to arrive so our system could go on. Model fine-tuning is required when applying to regions with different site typologies. So we had our model that was trained on Spanish and Portuguese data. When we wanted to apply that model to the UK, the performance dropped a bit, which was expected because the landscape in the UK is a bit different from the landscape here in Portugal and Spain. Also, the ilforts are a bit different. So we needed to do a small fine-tuning of the model so it would work properly on the UK. Expert archaeologists are needed to digitally validate the system detections from aerial imagery. So this work is quite challenging on the archaeologist because he has to validate thousands of detections, but this human-in-the-loop process is crucial to improve the vision system. This is one of those cases where human expertise is still required for these AI models to function properly. And finally, a human-in-the-loop approach showed strong promise in this domain, and we believe its value is broadly applicable to any field that requires this fine-grained discriminatory capability. And as for future directions, we want to explore archaeological predictive modeling to identify regions with higher archaeological potential. So instead of sweeping through the old data, we want to focus our vision system onto regions that have a high potential of having those archaeological sites. So this would reduce the processing time significantly. So this is something that we want to explore in the future, and also explore visual foundation models. This work that I present in this slide is quite recent. It was published last month. And the authors basically applied visual foundation models to try and detect archaeological sites. And from my understanding, the main advantages of these models are basically that they do not need to be trained. And also they are able to provide the reasoning behind each detection, which is quite interesting for troubleshooting any kind of mistake that the model is making, right? And we are going to restart this Odyssey project with a second edition in the next year, hopefully. We are still waiting for funding. So if you have any suggestion for our future work, please go ahead. So thank you for your attention. And if you have any question that I'm able to answer, I'm here.
Thank you very much, Daniel, for this very clear and interesting presentation of your project. And we truly have already several questions in the chat coming from Marek Bunzel. So I will start with the first one. In what regard are vision transformers superior to CNN in this application?
So I'm not an expert on networks. I'm more like of a user of these technologies. But from my understanding is that vision transformers are better than CNNs to capture the global context of the images, and that global context is quite important in some applications, and that is the case for archaeology because the elements in the landscape, the vision transformer needs to know what the landscape is, right? If it's a city, probably there is no archaeological site there, right? If there's a river, it's probable to have an archaeological site around because our ancestors usually built something around rivers and stuff like that. So whenever there's applications that require this global context, I think that vision transformers are superior. And also, if you have a lot of data, vision transformers usually also outperform CNNs.
And Marek would like to ask something. Please, Marek.
Yeah, thank you very much. I wrote the questions, and I'm sorry that I'm rushing you a little, but I will need to leave soon. Oh, I do not totally agree with the conclusions why are like a transformer superior to CNNs, because yes, well, if you have a lot of data, it's beneficial both for both networks, and they both can consider the context. But okay, so I will try to ask like the another question. You used like filtered digital elevation model on the input instead of the original. Why was that, and why like did you compare it with the DEM on the input?
You mean these images, right? The local relief models?
Yes, exactly. Because the filtering can remove some underlying information on this or distort, which is present in the digital elevation model. So did you compare the results if you use just the pure DEM on the input and the local model?
Yes, we tried at the beginning to just utilize satellite images, and we obtained worse results because most of these archaeological sites are under vegetation and
Yes,
under
but
trees.
I'm not talking about that.
Oh, okay, sorry.
Yes, I work with LiDAR for archaeology. We did like a detection of Maya buildings in Guatemala. I understand that, but it's like if you have the digital elevation model, you can apply various filters to visualize the features better. And I understand that you used on the input the filtered digital elevation model. It's not the original, like the point represents the elevation. Yeah, the value of the point represents the elevation. So that was my question towards the left picture in your slide now, not to the right.
If I'm understanding correctly, are you talking about this first digital terrain model?
Yes, yes. Okay, yeah.
This one?
Yes, exactly. Why not using that on the input by the local relief model?
Yeah, at the beginning we also thought, okay, maybe we can utilize this instead of applying a visualization technique, and we tried, but we failed. We didn't have any good results, at least on this digital terrain model. So we thought, okay, we need to try to highlight these microtopographies, and we searched for which visualization techniques are more common in archaeology, and we find this local relief model. That was also quite used in the literature.
Okay, well, we did use both, also various visualizations, and we concluded that the results are not significantly different, because actually if you use convolutional neural network, it can learn the filters. But okay, that's well,
yeah, at the time we applied the ULB5. We tried to applying different types of data to see which one is the most suitable, and well, we failed for the digital terrain model, so we discarded that option at the beginning of the project.
Yes, I got some better results, maybe with DeepLab version 3 or UNet++, but it's again like about comparison of the models, so it may be dependent. And I will skip my the question about the augmentations, but I would like to ask about why did you include like RGB orthophoto image on the input? Are some features there which depend on color?
Well, as I mentioned in the presentation, we wanted to replicate what human experts do during their digital validation. So when they search for archaeological sites, they have at least Archaeology, which is the company that we worked with. They have a lot of different types of data on their monitor, and they try to search for archaeological sites. And the main images that they utilize is a visualization technique, as the one that we used, and also the satellite imagery. And so because of that, we thought, okay, we want to use these two types of data because we think that the satellite image will complement the microtopographies that the local relief model has. Well, that was the main reasoning behind the choice.
Okay, yes, that's reasonable. But in my experience, it's always the best if you filter out all the information that's not necessary for the model to decide. So if there are no, let's say, crop marks or different colors in the vegetation that indicate presence of something, then maybe color is like their super. It's like too much. Yes, too much information which the model doesn't need, and so maybe it's always good to do some ablation study when you remove some parts of the input and try to find out like which are really important to get the output good.
Yeah, we wanted to do an ablation study, but as I mentioned in the presentation, this was done in our spare time, the Ilford use case. So we didn't have much time to do these robust ablation studies and see which step of our network, of our proposed system, impacts the final results. But hopefully in the next year we have the funding and the time to do that. But yeah, thank you for your suggestions.
Thank you very much. It was a nice presentation. Good luck.
Thank you. Now we will try to answer the next questions from Patrick. First question is, why ensure each burial mound appears in exactly one training patch? Is this to prevent unequal training weight or to avoid learning location-specific features?
Why they appear where? Sorry, I didn't get that.
You can have a look in the chat, but why it appears in exactly one training patch?
Why they appear exactly in one training patch? I don't think I'm understanding the question, but the burial mounds.
So Patrick maybe will elaborate a little more.
So
now you can unmute yourself. I clicked on allow microphone for you, Patrick, but it seems you're not able to unmute yourself anyway. That's true. Okay, one more time. Maybe now you can do it? No. But maybe we'll go to the next question.
I can try to answer, even though I didn't understand the question very well. But when we built the data set, these cropping windows, you can see them as like a window trying to search for an optimal position to make the cropping, right? So this does not have any predefined location to make the cropping. It's basically random coordinates. So we didn't. I think we don't have that problem of location specificity in the image. Because, well, the archaeological sites will be all around the image. They won't have a specific position. Okay. We thought about that. Okay, we don't want to crop archaeological sites where the archaeological site is in the middle, for instance, because of course that would bias the model. And so we opted for this random cropping way to do that. I don't know if that answered the question, but well, yeah, I didn't quite get it.
Okay, maybe then coming to the question number 2, how many of the 146 original training images contain no burial mounds? How did you select negative patch allocations from the massive LLM images?
So for the burial mounds, we put just 10% of background images. So only 10% basically have no burial mounds. But for the hill forts,
how did you select the negative?
We select a negative by basically applying that ULB5 model that was trained on the original dataset that only has images of with archaeological sites, and then we make croppings around the unused data, and we apply that ULB5 model into those cropped images to see if there's some possibility of having anything there. And if it didn't have anything, we just put in the final data set as a background image. And of course, we also had expert archaeologists to verify if, in fact, those background images do not contain anything. That was the process.
Okay, and the third question of Patrick is related to training versus inference asymmetry. So you use sliding windows, 50% overlap during inference, but unique patches during training. Why not use sliding windows for training with selective sampling, keep patches with plus or equals 1 burial mound plus 10% backgrounds, and this would show each burial mound in different contexts?
Well, that's kind of a data augmentation process, right? Well, we had several ways to do this type of data augmentation, and we opted for this traditional one and this copy-paste one. But of course, we could use the one that you are suggesting for sure. But at the time, we didn't think about that. But it's something that we will keep in mind for next year, for sure.
So I think we answered now all the questions. If anyone has any more, you can still write. I would maybe just ask a quick question as well. From your experiments, we understood the landscape characteristics play a role. So could you maybe tell us which landscape characteristic make the biggest difference in how well this kind of model could be adopted in other regions?
Well, the main characteristic in the landscape that we noticed that our model performed better is when there is no vegetation, right? Because if there is no vegetation, this approach of fusing the local relief model and the satellite image is ideal, because we can see how the landscape looks like and how the archaeological site looks like in the satellite image. But of course, when there's vegetation, this is quite less inefficient. It's quite more inefficient to make these kind of detections. So that's probably I would say the main landscape characteristic that would improve our results here.
Okay, thank you once again, Daniel, for sharing your research with us today, and thank you to everyone who joined the session and contributed with questions. We will send out a short feedback form, and we would really appreciate your input. It helps us improve our webinar series. The recording will be available soon on the NCC Slovakia website and YouTube channel. If you're interested in continuing with our LLM series, we invite you to join our final webinar of this year on December 11th, focusing on the Polish model Bielik AI. So wishing you all a great day, and we hope to see you again soon.